Hello, my calculus doing friends. This is the second part of 5.2. And here's an example, and I'm sorry, this example is not in your notes, but find the volume of the solid obtained by rotating the region bounded by y equals x to the third minus 2, and also y equals -1 and x equals 2. And you're going to revolve that about the line y equals -1. So it was one I wish was in the notes, but didn't get it in there. And so if you're seeing this video in a subsequent semester, how do you say that? It'll be in the notes. So the first job is to draw it. So I'm going to make a quick sketch of this. So down here at -2, it's going to cross through. And then at y equals -1, going to have a line going across there as parallel as I could to the x-axis, my drawing skills. And then at x equals 2, now I kind of want to know where that crosses right there so that I'll know where x equals 2 is on my scaled problem drawing, right? And so how I would know where that cross is y is -1, and that would be crossing this graph right here. So I can plug that in. -1 equals, because that's what y is there, x to the third minus 2. And how I could solve that, add 2, and that's at 1 equals x to the third, so x equals 1, right? And so that doesn't look like 1 on the distance, and so I'm going to fix up my drawing there. So that kind of sometimes happens to me, is that I start making a pretty loose sketch, and then I start caring about where things are really crossing. So I'm going to have 1 here. Was that line here at -1, and right here. So this curve should be going through there like that-ish, okay? And then now if this is at 1, then 2 is somewhere over here, and that's what we had, x equals 2. It's about to get big on me like the other one did. Okay, and then we're supposed to rotate. It says the revolve about the line y equals -1. So here's the line y equals -1. And this one didn't ask me to draw the solid and try to draw a disc in there. It's just asking me to find this volume. And in fact, it might just be a setup one, because I'm realizing this video is going to get really long. And so we might just set it up, and so this is what we're going to be revolving. That's the region we're going to be revolving. And so what we want to find out then, remember how your formula goes, since I'm going around something parallel to the x-axis, my volume, if you use the disc method, and you're saying if you use the disc method, there's another method, and yes, my friends, there's 3 methods. So we're going to be looking at the disc method is what we're looking at right now, and the volume is equal to pi r squared dx when I'm going around something that's parallel to the x-axis or the x-axis, in this case parallel to the x-axis. So now I would like to draw in there my typical r. And where your typical r goes, and I know I haven't drawn the whole, I haven't revolved this and drawn the solid over here, but my typical r, where it goes is from the axis of rotation. So here I am on the axis of rotation to the curve. So there is a typical r. And before, because we were going around the x-axis before, that the r just turned out to be our curve. But that's not what it's going to be here. And so we're going to have to be more careful than that. And so remember the distance that goes from the x-axis to the curve. So from the x-axis to the curve, do you guys remember what that distance is called? From here to here. That distance is called y. And so that distance from the x-axis to the curve is called y. And in fact, in our case, we want everything in terms of x. That distance is x to the third minus 2. But that distance from here, the x-axis, to the curve is not r. R is the distance from here all the way to there. And so you might be screaming at your TV set right at this moment. You might be screaming that r equals, remember this distance here was called y, right, plus 1. Because the distance from here to here is 1. The distance from here to here is y. The whole distance is r, right? And so I haven't drawn this as lovely as I could. You know, my mom, the only person watching these, will give me a call. Maybe my dad's watching them too. That's the whole distance is r. And remember that y is x to the third minus 2, so plus 1. So r equals x to the third minus 1. That's what our r equals. So our volume then would be the integral from pi, r is x to the third minus 1 squared dx. And what I would need to do in order to find the antiderivative of this is write it twice and use FOIL. I'll end up with 3 terms after I use FOIL, and I'll be able to easily integrate that whole thing. Now my r's are going to go from here. This is where they're crossing here at 1, which we had to find that out. Remember when we did a little math to find that out, all the way to 2. And so our r's are going to go from 1 to 2. We're going to run x, right, and it's going to create a radius from 1 all the way to 2. And so, so that'll find us the volume of this figure. Of course, I didn't draw it in three dimension, but if I did, it would look, you know, like that, right? And you make the circular thing on it. And so you could easily find this, this volume here. And so we'll go on. So that's that story on that one. I wanted to make sure that I had an example that went around an axis other than the y-axis. For whatever reason, I probably have it later on in the notes somewhere, and I was like, oh, we better do one. Okay, so right here is how to find the area of a washer, because you might be saying, well, what if when I make my slice, what if it's not solid? What if there is a hole in the center, right? And that's called a washer when you have that, and that can certainly happen. And how you find the area on a washer, so if I want to find this area here, that area right there, a donut, right? Ooh, donut. Is there any donut shops open? Then what you would do is you would take pi and radius squared, and what that's going to find when I do that is the area of the big circle, right? So the pi radius squared is going to find the big circle, and what I would like to do is I would like to subtract out, minus out, the little circle, right? And so that would be minus and then pi little r squared. And then of course you could factor out a pi, and then that would be big R squared minus little r squared. And so we're going to be using that. So I told you there were 3 methods. This is going to be the second method. Now it's not appropriate to use all methods on all problems, but this is the second method that we're going to learn. And so the basic technique, if you're going around the x-axis or parallel to the x-axis, the equations need to be solved for y. You make your graph, you sketch it out, you say what your typical r is in your typical big R and your typical little r. Remember that the radius goes from the axis of rotation to the curve. And when you have a washer, there's going to be 2 curves. And so there's going to be the inside curve here and the second curve. And so this is going to be from the axis of rotation to my outside curve and to my inner curve. And so that's what my r's will be. My x and my y are the same distances that we already learned about. And then my formula for my volume will be the area, which is pi times the radius squared minus the little radius squared, just what we got here. And then dx when you're going around the x-axis. and dy when you're going around the y-axis, but everything else the same, or parallel to the y-axis or parallel to the x-axis. Okay, so we're going to give a try. And you're like, hot diggity dog. And so I'll draw this one here, and then I'll get my my computer over here in my boomer fashion so that you can see what we got going here. So this is example 5 out of your book, and I'm doing example 5 from the book because the book provides the lovely drawings. So here's y equals x, and y equals x squared, when I draw it, looks like this. And what we're going to be rotating is the area that is trapped by the two curves. So the only area trapped by the two curves is that little area right there. And we're going to be rotating it around the x-axis. So I know if I use a disc or a washer, either one, I don't know which one I'm going to use yet, those are the two methods I'm learning about, that my integral will be dx because I'm going around the x-axis. And so I haven't put what I'm going to integrate yet because I'm going to figure that out. So I want to, this is figure 3, so I want to show you it here. In boomer fashion, right? Putting my computer underneath my thing, and so that we can see it. And you could see that this is the drawing that I have currently, and over here is where they're going to make the three-dimensional drawing so that we can see the three-dimensional drawing when it's rotated around the x-axis, so that you can see that when I rotate this so that you can see it, it actually has a center that's hollow. And that washer, so you can go and certainly look at that and make this washer go, move this washer around. And I'm trying to grab the washer, but then that's not how you do it. When you move this washer around, and it moves it over here as I move that washer, and you can see the solid. You can see the hollow center even better as you rotate it and look at it. Okay, so that's what we're trying to find the volume of. Okay. And then I have to plug my computer back in. So I have to unplug it to do that and then plug it back in. It's just so crazy. So remember where your radius goes. I'm not going to draw it in 3 dimensions. And so, ooh, this is my opportunity to go for a walk.
Call from Patrick.
Hello, are we going walking? It's a good time. Okay,